design by contraction is a technique for simplifying the logic. And if you have, for example, some of the inputs are constants like zeros and ones to a circuit, then you can use these inputs, you can propagate these constants, and you can simplify the logic. So we can convert, okay, a circuit to a more simplified one. I'm going to show you two examples. The first one will be about how we can design a circuit, an incremental circuit that can increment a certain input, let us say by 1. And I'm going to show you another example about how we can design a decrementer. Okay, so these are my two examples. Like, let us design a circuit, okay, that is called an incrementer. So an incrementer is a circuit that takes a certain input A and adds 1. So the sum here is calculated as A plus 1. So there is only one input A, and I would like to increment it by 1. Okay. Now we can actually say that the incrementer is a special case of an adder. So I can use an adder to add A plus B plus a carry 0. Now B here can be made 0. So notice that B here is 0. This is B. And I can make C0 equal to 1. So that's here is my C0. That's actually C0. So by having C0 as 1, you are adding C0 to A, and this output, the output of this circuit will be just an increment. Okay. You can, of course, make it n-bit adder if you would like to have A consisting of n bits. Here in this example, I'm showing only 4 bits for A. So A consists of 4 bits, and we would like to add 1. Fine. Now, let us take a look at the circuit here. So we have 4 full adders. This is a ripple carry adder that we have studied before in the previous lecture. Fine. So let us take a look at this AND gate here. This AND gate. So when you AND A0 with 0, so here I have one of the inputs is 0. So when you AND with 0, what do you get? What?
0. 0.
0.
You get what? Again, I did not hear you. Sound? Exactly. We get the output 0. So do I really need an AND gate to AND with 0? Do I really need an AND gate if one of the inputs is always 0? Do I really need an AND gate for that?
No.
We already know the output, exactly. So in fact, these AND gates here, these 4 AND gates, I don't need them because I already know that their outputs are all zeros, right? So this is simplification of the logic. So we are simplifying the logic because I know that one of the inputs is always 0. So I have actually a constant input. Like, now tell me about this XOR gate. These 4 XOR gates, these XOR gates. What are their outputs? I'm XORing with 0. So when you take A3 and you XOR it with, let us start with A0. When you take this A0 here and you XOR it with 0, what do you get the output of the XOR gate?
A0.
Exactly. The same thing can be said for A1, for A2, and for A3. So therefore, all of these XOR gates are not really needed because I already know what's the output. So when you have one of the inputs here is a constant, I already can tell what's the output. So the output is A0. Precisely. Right. Now this AND gate here, look at this AND gate. Okay. Before that, let us take a look at this. Okay, let us take a look first at the AND gate. Now, when you take A0 here, okay, and you end it with 1, what's the output of the AND gate?
A0.
A0.
Exactly. And you take actually this A0 here, and you OR it with 0. What do you get?
A0.
A0.
So therefore, I don't really need the AND. I don't really need the OR. I don't really need these 2 gates. How about this OR gate? Do I need this OR gate? This OR gate, do I need it? This OR gate here, do I need it? Do I need this OR gate?
Yes.
Well, we have one of its inputs is 0. So when you OR with 0, what do you get?
Always 0.
No, you don't always get 0. You get actually this input here. So basically, you can take the second input and you can propagate it to the output. So I don't need actually an OR gate to OR with 0. So in fact, we can do a lot of simplifications. So here we have, let me clean up my handwriting. So notice that first for the OR and this AND gate, we have removed them because I already know that the C1 output carry 1 will be simply equal to A0. I can actually remove these OR gates because I'm ORing with 0. So therefore, we can just propagate the output of the AND gate can be propagated directly to the output. You can see here the output is propagated directly to the output because I have one of the inputs is 0. So you can actually have any value here at the output of the AND gate. We propagate it to the output. So this will result in further simplification of the logic. Now, again, here we have one more. Let us take a look at this XOR gate. So this is A0. This is 1. Notice that here C0 is equal to 1. That's here my input C0. Right? So what will happen when you XOR A0 with 1?
A0 prime.
Exactly. You get A0 prime. So S0 is equal to A0 prime. Do I need a XOR gate to produce A0 prime?
No, we just need an
No.
inverter.
An inverter, yes, exactly. So the XOR gate is a complex gate. We can replace it with an inverter that will invert my input A0 to get A0 prime. So we have seen actually a lot of simplifications. So let us now redraw the circuit. Okay, so we can see that the output here is A0 prime. So now we can simplify the circuit. Now this is now a simplified incremental circuit. So I removed actually my B input, which actually are all zeros. I removed C0, which is always 1. I replaced the first full adder. I replaced it just with an inverter because I know that S0 is A0 prime. Right? And notice that here I only need one XOR gate and one AND gate to produce the sum bit and the output carry. That's it. So now my full adder, it became a half adder. So this is a half adder. This is a second half adder. And this is a third half adder. So the half adder consists of XOR gate and an AND gate. And we can produce, okay, I can design now my incrementer, okay, using these 3 half adders. That's it. So now this is actually the symbol of my incrementer. The sum is equal to A plus 1. My input consists of 4 bits, which is A3 down to 0. My sum consists of 4 bits, S3 down to 0, but I can also use C4 because we might also produce an output carry. Okay, so we have simplified the logic. That's really the idea of design by contraction. Okay, is this clear? Now that was example number 1. Saud, you have a question?
I just said it's clear.
All right, good. Now let me give you a second example. Suppose I would like to design a decrementer. So I would like a circuit that will calculate its output here as A minus 1. Okay, I would like to design a circuit that calculates S is equal to, the sum is equal to A minus 1. Now we know that minus 1 in the 2's complement representation is represented here as all ones in binary. Correct? That's minus 1. It's all ones in binary. So if A and B consist of 4 bits, I will have 4 bits that are all ones. So now we replace by B here with 1s. and I replace C0 here by 0. Now, can we do simplifications? Do I need this AND gate here? Do I need this AND gate? Yes or no?
No.
Why
just
not?
A0. It's just
Because
A0.
the output is always A0. So A0 and 1 is A0. So we already know what's the output of this AND gate. In fact, I don't really need any of these AND gates. So we can get rid of them. And therefore, we can say that the outputs will be A0, A1, A2, and A3. So this is my first simplification. Now, how about this XOR gate? This one here.
A prime 0. Or
Yes.
A0 prime.
A0 prime, exactly. In fact, I don't need all of these XOR gates because I already know that their outputs are inverted. So I can replace them with inverters. Okay. So I can replace the XOR gate with an inverter. Of course, the cost of an inverter is much less than the cost of XOR gate. So we can simplify the logic. Right. How about this XOR gate? Do I need this XOR gate here?
No.
No. It's just
So when you
A0
XOR
prime.
A0 prime with 0, what do you get?
A0 prime.
Exactly. I already know this is actually output here is A0 prime. How about this AND gate? What's the output of this AND gate?
0.
0. Exactly. What's the output of this OR gate?
A0.
A0.
Exactly. So do I need this and this OR?
No.
Okay, so let us remove them. Let us remove them. Right. So now what we have done is that we have eliminated many gates. So let us redraw the circuit now, the simplified circuit. Here is my simplified circuit. So we have removed, so in the first full adder became just an inverter. So we know that here as 0 is nothing but A0 prime. I just need an inverter. So we had actually many gates. So now we replace them with just one inverter. This is for the least significant bit, for S0. For the remaining ones, we have replaced the first XOR gate here with inverters. And we have simplified the logic. Okay. Right. Now, let us take a look at this and this OR. Let us write the equation for C2. Can you tell me what's the equation for C2? What's the equation for C2?
A1 or
Yes.
A1 prime C1.
So let us write it down as A1 or
A1
A1
prime
prime.
C1. C1.
Okay. Can this equation be simplified according to the properties of Boolean
A0.
algebra?
C1 is A0.
No. About C2, can we simplify this expression?
Yes, we can delete A1 prime.
Exactly. I don't really need this. And what does it mean? If you remove, okay, the A1 prime, so it can be simplified to A1 or C1. So what does it mean?
We can delete the AND.
Exactly. Thank you, Saud. So knowing the properties of Boolean algebra, I can delete all of these AND gates. So this is further simplification. You see what we have done? Right. Now, let us take a look at, okay, so let me clean up my ink. So what we have done now, using the properties of Boolean algebra, because this is A1 prime and this is A1, okay, we were able to get rid of the A1 prime and we're able to get rid of the AND gate. Not only for A1 prime, but also for A2 prime and A3 prime. All these AND gates were able to actually to get rid of them. Okay, so that's really good. Now, here we have an inverter. Here we have XOR gate that has one of its input to be inverted. I can move this inverter here to the output, and I can invert the output and remove the inverter. So we can replace the XOR with an exclusive NOR, and the result will be like this. This is also further simplification. So notice that we have removed the inverter, and we have replaced the XOR here by an exclusive NOR. Okay, this will give me exactly the same output. So now you can see that we have simplified the circuit for the decrementer. Okay, and this circuit can actually calculate S is equal to A minus 1. So it can decrement A by 1.